And welcome back to 12.3, where we're looking to wrap up our discussion on stoichiometry. In this whole chapter, what we've been trying to do is trying to take a certain amount of reactant to a certain amount of product. We first started off by assuming that everything was in a perfect ratio and all the reactions worked perfectly. Then we said, well, that's not really what happens. Oftentimes you have more of one reactant and less of another, and something runs out first, and then that determines how much reaction is actually going to happen. Now we're going to take a step and say, okay, well, knowing that something runs out first, sometimes reactions do not proceed perfectly. For example, campfires will often go out before all the wood is burned. You've probably noticed that sitting around a campfire at a campground or on the beach or something like that. Well, chemical reactions in the lab may not go to completion either. So in that case, all the product that you expect to be made might not necessarily be made. Now, there are two reasons that all of the expected product might not be produced. One reason is what is called an incomplete reaction. That's just, for example, when the campfire goes out, the reaction just stops. It might not have enough energy. There are a variety of reasons why the reactions might stop, but they simply do not proceed. The other reason is what are called side reactions. Side reactions are when other products are formed. For example, when we burn things, say a hydrocarbon or a carbohydrate, carbon dioxide is expected to form. But sometimes instead of getting carbon dioxide, you might get carbon monoxide, just CO. In that case, you're not going to get all the carbon dioxide that you would expect because a lot of the carbon is already wrapped up in a different compound, and that's not in the balanced equation. So that's what is called a side reaction. So therefore, we want to express how much product we actually make compared to what we expected to make. And here's the equation. Of course, a percentage is going to be the same regardless of how you use it. Percentage is always going to be part divided by the whole times 100%. And so the part is what we actually get, what we call the actual yield, divided by the whole thing, which is what we call the theoretical yield, times 100%. So for example, if we expect to make, say, 8 grams, all right, that's our theoretical yield, but we only make 4 grams, obviously then our percent yield would be 50%. We only got half of what we expected to make. So let's go ahead and take a look at a few examples here. With example number 4, it says if you only made 100 grams of the copper 1 sulfide, which is Cu2S, in example number 1, what is the percent yield? Well, as you flip back through, you'll notice that we expected to get 125.2 grams of our copper sulfide. So that it was the expected yield, 125.2 grams. In fact, if we scroll all the way back to example number 1, we'll show you that. All the way back and all the way back. Alright, here it is, actually right here. We did the calculation, and with a cloud around it, we expected to get 125.2 grams of our Cu2S. So that is our expected or theoretical yield. Now as we make our way to the back page here, again, we only got 100 grams. So that was our actual yield. Times 100%, and it looks like we get 79.9% yield. Now, is that good? 79.9, would we round that up to 80% and say, well, you get a B minus for your yield? No, not necessarily. In some reactions, you expect to get nearly 100% yield every time, so that 80% yield is actually horrible. In other cases, reactions might only expect to get 50% yield, and if you had 80% yield, they're going to give you some type of award for that, for figuring out how to get such a good reaction out of it. So the percentage doesn't necessarily indicate how well the reaction proceeded. It just simply states how much did you get compared to theoretically how much you should have gotten. Example number 5 says, if you only made, let's say, 12 grams of rust, Fe2O3, in example number 2, what is the percent yield? Well, again, flip back, and you'll notice that you expected to get 14.3 grams of the rust. Where did that come from? Let's scroll on back. And here was the calculation for that particular question, where you took the iron and formed the 14.3 grams of rust. The excess oxygen could have produced the 66.5 grams, but you run out of the iron before you get there. So 14.3 grams of rust is what's expected. Now, as we go back down to that last page, in this case we only got 12 grams of rust. Times 100%, and it looks like our yield in this case would be 83.9%. And finally, go ahead and pause this if you want to try this on your own. Let's say that you only made 20 grams of ammonia in that last question in example number 3. What is the percent yield? Well, our actual yield is 20 grams. We expected to get 30.4 grams, so therefore our yield is going to be 65.8%. So reactions do not necessarily go as planned, and so the percent yield is simply going to express how much product you made compared to how much you could have made or how much you would expect to make. All right? That concludes Chapter 12.